In this video, I'm talking about arc length, which is oftentimes the first of the real C topics that you study in a Cal BC course. Okay, this one is not included in Cal AB. So, arc length, say this is a continuous graph, and I want to find the length of it. Actually, I think you need a little more than continuous. You need it to be rectifiable, which, we're not going to really go into what curves are and aren't rectifiable, but just say that it needs to be reasonably smooth. And I don't know that you've come into, we looked at sine of 1 over x last year. It was the one that got really wiggly towards the origin and at the beginning of this year. That one, it gets so wiggly that you really can't, well define an arc length on even the open interval. So but most curves, and all the curves that we're going to encounter in this class, are going to be curves that we can find the arc length of. So what I'm going to do is I'm going to just talk about a small piece of the arc length, and then we're going to add them all up, right? Because it all goes back to the idea of the Riemann sum. Okay, so we're going to figure out what is the length of this piece, and then we're going to add up a bunch of these as we let x run from A to B or whatever. Okay, so I'm going in. I'm going to look closely at this. Okay, and so this is the thing that this hypotenuse, this looks like a right triangle. This hypotenuse is what I'm going to add up a bunch of to get the total arc length. So I'm going to call this a small piece, a delta p, a small piece of length. Okay, and then this is delta x, and this is delta y. Okay, as delta x gets towards 1, then delta y becomes dy dx, if we're just on the trajectory that the curve is going, starting there. But I'll get to that in a second. One thing that we know is true about this small right triangle is that delta p is going to be the square root of delta x squared plus delta y squared. That's true for sure. And then we're going to say that the arc length is going to be equal to the sum of all of these delta p's. Okay. So this is the sum of these square roots of delta x squared plus delta y squared. Okay, but I want these pieces to get really small and to add up infinitely many of them so it turns into an integral. But what is this thing missing? What part of the integral does this thing not have? Yes, it's me just whispering it. It's missing like something out here, right? Yeah, a dx. Okay, but it would be a delta x in this case. It's like, what do I do? And besides, what is even delta y? What am I going to make of that? And delta x, what do I do with this? And so this is where you have to know to multiply by a clever form of 1. And so I'm going to multiply by delta x over delta x. But then, what am I going to do with this delta x in the denominator? That's not really helping. What I could do instead is say that, as I'm copying this down, the bottom delta x could be the square root of delta x squared. And then I could use one of those, old-fashioned radical properties and kind of divide in that square root of delta x squared. So and now this is looking closer to something that could turn into an integral as delta x got really small. And I'm going to, it depends on how you look at it. You could look at it as distributing a 1 over x squared, or you could, maybe call it the heart-shaped thing, I've been in my class for a while. But I'm going to do this. I'm going to divide. And that's going to be the sum of the square root of delta x squared over delta x squared is 1. And then delta y squared over delta x squared. Maybe I could do it like that. And then as the number of as the number of small pieces of arc length goes towards infinity, and delta x goes towards 0, this becomes an integral, right? It's going to be just between two x values, so that's square root. The delta x becomes dx. 1 is going to stay 1. What is delta y over delta x squared going to become, do you think? Or what would delta y over delta x become? dy dx. Okay, yeah, so it's 1 plus dy dx squared dx. And this is the Arclength formula. So yes, this is the, officially approved Arclength formula. And the good news about this is that almost always, really almost always, you take a derivative of a thing, you square it, and you add 1, it's not going to be a perfect square. Okay? If you had something whose derivative was tangent, and you square tangent and add 1, that is a perfect square. It's 1 plus tangent squared is secant squared, I think. Or maybe 1 plus secant squared. No, I think it's 1 plus tangent squared is secant squared. And, thank you. And so, but then you're taking the square root of secant squared and you're looking for an antiderivative of secant, and you're not really that much better off. Okay, so the great news is that this is almost always either a calculator question or a set it up but don't evaluate it question. And that's good news for us. I may record a separate video of Arclength examples, but this video I'm just really showing you how this came to be.